Okay, we're going to get into the photoelectric effect where we left off in class on Friday. So start off with, oh, shucks. You got time to think about this because I forgot to start up the... and I started up wrong because I got in a rush. C'est la vie. Yes, it's a song as far as I know. Dude, I can spell it. I'm pretty proud. All right, we're almost there. And you can answer starting now. What does it mean if a quantity is quantized? We had this question on Friday, so this is just checking to make sure that the people who didn't understand it then understand it now. So, let's see. Jonathan answered from outside. Jonathan, when is your recital?
What?
When is your recital? I'm inviting all of my friends here to your recital.
On Sunday?
This next Sunday?
Yeah.
Okay, next Sunday at 3 p.m.
It's at UNL.
At UNL, downtown. Everybody going to go, right? They're there. It's set on your Facebook page to invite everybody, so.
Yeah, sure.
He doesn't sound really down with everybody coming. Okay. You getting close? Okay. Oh, there we go. Okay, so we only had one dissenter. Whew. Once again, just like last time, it shows them on the wrong line, and I was like, really? Everybody said the quantity can only have negative values? But it's the spacing here. Those are zeros, not an 8. So all but one said the quantity can only have discrete values, and that is correct. That's what it means for it to be quantized. So it's not that the quantity is small, but in practice, quantum theory is applied to small things because that's the only time when we see different results. Just like with relativity, relativity applies always. And it's just the measurements in one reference frame compared to the measurements in another reference frame. But the only time we actually use the relativistic calculations is when things are going really fast. So some people say, relativity is the physics of things going fast. Well, special relativity. But it always applies. It's just that the only place where you have something distinctly unique is when you have things that are going really fast for special relativity. Okay, so I ended on this slide. Planck said that energy from light sources that are giving off light because they're hot. So he was very specific. He gave what we call his quantum hypothesis. If the light came in packets of energy, so at a given frequency f, you can have 1 times hf or 2 times hf or 3 times hf as the energy in that frequency, then he could explain with physics theory why his equation was correct. And so that h is called Planck's constant. And, I've lived long enough saying it Planck that now it sounds right to me. But, of course, as a Native American, when I was in college and high school, I thought this was Planck because, that's what it would be in English. But he was German. Okay, so the photoelectric effect. In 1886 and 1887, Heinrich Hertz did some experiments to test James Clerk Maxwell. James Clerk Maxwell had said that after he was able to take all of electromagnetism and shrink it down to just 4 laws, that those laws predicted that you could have a wave formed from electric and magnetic wave, or you can have an electromagnetic wave. And that because his calculated speed for the electromagnetic wave was the same as the speed that was experimentally measured for light, that light must be an electromagnetic wave. And as I said in class, that's a pretty sketchy reason. And so Heinrich Hertz is the person who sat down and said, okay, I'm going to make electromagnetic waves. So what he had was a little spark generator. He basically had an antenna, and he had something here in between that was giving you positive and negative voltages, and it would arc across there. Okay, so I didn't draw this exactly right. it would arc here, and that arc, I should red and show, and that arc is what would make the waves. Each time it arced, you would have a wave somehow. And so he was making his electromagnetic waves this way, and he found that the electromagnetic waves have the same diffraction and refraction properties that light waves have. And based on that, he said, okay, it makes more sense to me now that light and electromagnetic waves are the same because they have these same properties, can travel through a vacuum, etc. So when he was doing this experiment, he has a notation in his book. Remember, when you're doing your labs, in your lab report, you're supposed to be keeping notes as you go through, right? You're just not just writing down, okay, this is the result of my experiment. You're saying, okay, this worked well, this didn't quite work so well. And I had to make this adjustment. Well, one of the things he noted was that when he polished these little globes that the arcs were going between, that shining light on it would make it so the arcs came more easily. That there was some relationship between the arcs and shining light on the metal. And he didn't know what it meant. It was just a notation in his lab book. But because he properly noted what he was doing, he gets credit now as being the first person to observe the photoelectric effect. So just a little, a little reason why you're supposed to be keeping track of what you're doing in experiments, right? Because that's, in real science, an important part of the process. If you don't do that, you probably have lost a lot of data that potentially could have helped. So 1905 is when Einstein enters the scene. Einstein wrote 3 papers. I think I already talked about those 3 papers when we talked about relativity. And this one here is the one that he got the Nobel Prize for. So this one here must be big, because you know that special relativity is big. So what did he say? He said that Planck, his hypothesis is right, that the light is coming out as particles, not as waves. And of course, you make such a bold proclamation, you have to have some reason behind it. And so Einstein proposed an experiment. As far as I know, the experiment had not been done, but he proposed it because this was an experiment that would separate the 2 theories. As far as I know, Einstein never did any experiments, right? He did a lot of thinking, not experiments. Experiments were for the lesser people. I got my PhD in experimental physics. So he proposed an experiment where you take metal, so here's a piece of metal, and you shine light on that metal. So you have light shining on the metal. Now, it was well understood that if you shine light on the metal, you are going to have electrons that come off. That was not surprising. That was known. And so you shine the light on, and you're going to have electrons liberated from the metal. Where did these electrons come from? You can say the words I just said, or you can be a little more specific. They came from the metal. Specifically, these would be conduction electrons in the metal. The electrons that were not bound to a specific nucleus, but were pretty free to move through the metal. Now, these electrons are going to have a certain energy required to make them break free. If it wasn't, they would just freely leave all the time, right? So there's got to be a certain energy that requires them to leave. Just like when we talked about breaking water molecules away from a liquid, there's a certain energy necessary to break them free. And so we call that the work function. And that work function would vary with metals, right? So if you have aluminum, it's going to have a different work function than if you have brass. But you have a certain energy that's going to be lost, the energy that has to be given to the metal for the electron to leave. And so that's the work function. And so this electron is going to come off with a certain amount of energy. And the questions that Einstein was asking were about the energy the electron has. Now, according to wave theory says, and well, especially people teach to, the intensity of the light is proportional to the electric field squared, right? And so wave theory said that if you increase the amplitude of the electric field, you're increasing the intensity, which is the energy per unit time per unit area, hence the amount of energy that's available to be absorbed by that electron. So wave theory says that if you increase the amplitude of your electric field, make it brighter, more intense, then that electron should come off with a higher energy. So wave theory we call that electron a photoelectron because it's an electron that was released because of light. Photoelectron has energy increase proportional to intensity. So if you raise the intensity, you should raise the energy of that electron. That's what conventional theory says, wave theory says. I say conventional because at that time it was the convention. Now, particle theory, on the other hand, particle theory says that the energy of a photon is equal to HF, and it's really unlikely that more than one photon would ever be absorbed by an electron. So barring the situation where two photons are absorbed by one electron, the photoelectron energy increases proportional to the energy here increased frequency, so it's proportional to frequency. Okay, frequency I can't read. So basically, according to Einstein, if you go from red light, lower frequency, to blue light with a higher frequency, the energy of that electron should be higher. Whereas according to conventional theory, the wave theory of light, changing the color doesn't matter. But if you change the intensity, if you make the light brighter, then you should have more energy in the electrons that come off. Now there's a secondary test. That's the first test and the one we generally consider the most. But a secondary one is, what happens according to wave theory if you change the color? Nothing. What happens according to particle theory if you change the intensity? Okay, you have more electrons coming off. Each electron still has the same energy, but you have more electrons. So according to the particle theory, the number of electrons coming off is proportional to the intensity. The energy of the electrons is proportional to the frequency. According to wave theory, color, frequency doesn't matter, and the energy of the electrons is proportional to the intensity. So you have very distinct predictions from these two. And of course, I've gone through everything on one slide. Now let's go through 4 slides that summarizes what I just said. Photoelectric effect, light hits the surface, electron comes off. Traditional apparatus like we're going to use in lab tomorrow, you have a metal plate, and inside that metal plate you have, that shows a single wire to collect photoelectrons. Light hits the metal plate, electrons come off. If the voltage difference between that wire in the center and the external piece of metal is small, then you have enough energy for the electron to come over and be collected by the wire. But as the voltage difference gets bigger, you'll get to the point where the electron doesn't have enough energy to cross over. And so what you do is you measure what that maximum voltage is, and so you'll have the kinetic energy max, the maximum kinetic energy of an electron that's coming off is equal to the charge of an electron times the voltage difference between the two pieces. So I'm going to put delta V just so it doesn't look like the unit electron volt. So delta V is the voltage difference between this and this. I actually called it VS here. So to be consistent with my picture, I'll put VS. So you measure the voltage that stops electrons from coming over. We call it the stopping voltage. That's why it has the VS. It's not source, it's stopping. I made a mistake. So you measure that stopping voltage, the voltage that will stop electrons from coming across, and that tells you what the maximum kinetic energy is. And so with this device then, you vary the intensity of light, you vary the frequency of light, and you check the outcomes versus theory. So this one is going through what the two theories say. The maximum kinetic energy is independent of intensity of light according to the particle theory. Depends on the intensity of light according to the wave theory. The experimental results, what do they show? They show exactly that. They show that there is a certain frequency that we call the cutoff frequency. And below that frequency, you don't have any electrons that come off. And then as you raise the frequency above that cutoff frequency, the energy of the electrons is proportional to how much you change the frequency from the cutoff. Now we can come up with a good theoretical explanation for that. We have a photon coming in. What's the energy of this photon? Going to Max Planck. It's h times f, right? Planck's constant times the frequency. And then it hits the metal, and an electron comes off. Now this electron has kinetic energy is equal to the energy of the photon minus the amount of energy necessary to break free of the surface, which we call the work function. So I'll put W sub 0 for that work function. Now I said that's the kinetic energy. We have to be a little clearer on this just for sanity. That would be the kinetic energy if that electron was right at the surface of the metal, and when the light hit it, it leaves the surface and never hits anything else. In reality, you have electrons all through the metal. The light's probably going to go some certain distance into the metal before it's absorbed by the electron. And that electron could go any direction, bounce around a few times, and then finally escape. But if it bounces around a few times, what's going to happen to its kinetic energy? It's going to lose some. So its kinetic energy could always be less than this value. This is the maximum value it could have. And so to make sure that we've covered our bases, we put the kinetic energy maximum is equal to the energy of the photon minus the work function. Substituting in the energy of the photon to that equation, we have Ke max is equal to HF minus that work function. So that's the particle theory equation for what we should have. So now if we look at that, we can say, what's the minimum possible kinetic energy anything can have? 0. And so we will define the cutoff when kinetic energy max is equal to 0, right? You shouldn't be able to get any electrons off if the maximum kinetic energy is negative. And so then we can just solve that. So that gives us the frequency for cutoff is equal to that work function divided by Planck's constant. So we can calculate the theoretical cutoff frequency if we know the work function, how much energy is required to break an electron free. And then this equation, if we plot the maximum kinetic energy on the vertical axis, so this is the vertical, this is my y variable, and frequency is my x variable, what should that look like if I graph it? Should be a straight line, right? That's the equation for a straight line. And so this graph exactly looks like what we predicted. And notice here it has marked minus phi on that axis. Why minus phi? because they just use the symbol phi here for the work function. And so if you, in theory, had a frequency of 0, the kinetic energy max, in theory, would be minus phi. But it's dashed lines because that doesn't actually happen. It's not possible. So by looking at this data here, you can determine the work function and verify, hey, that agrees with the idea of the particle nature of light. And furthermore, from the slope, what should the slope of that line be? Should be Planck's constant. So you can find Planck's constant by looking at that graph, which you're going to do in lab tomorrow. Okay, I've already gone through the threshold frequency, that F0, that we've already calculated. Don't need to spend time there. There is a time delay. Let's not worry about that at all. Instead, let's go to a clicker question to see who was listening. Who originated the idea of light being quantized? Okay, this is most disconcerting because I have been talking up here. And we have far less than unanimity here. Nate, give us an answer and a reason.
I chose C.
Okay, Max Carl Ernst Ludwig Planck. That is his full name. Why'd you choose Planck? Because I remember you saying it, because I said it many, many, many times. That Planck was the one who came up with the idea. So now 5 people said Albert Einstein. What did Albert Einstein come up with? He said it was right and not just an idea, and an experiment to test it. They both got Nobel Prizes related to this. Hermann von Helmholtz had nothing to do with this as far as I know. Neither did John William Strutt. I scratch my head to wonder how those answers came. Okay, next question, one I haven't talked about. This one here is not an indicator of if you've been paying attention or if you've been wasting your time. Okay, we had 12 that said high energy photons, 2 that said low energy photons, 0 that said low energy particles, and 5 that said high energy particles. The last 2 were not photons. Okay, so the majority here are correct. X-rays are high energy photons. So why do we call them X-rays and not just say, hey, those are gamma rays? Or those are ultraviolet. The term X-ray refers to what produced them. Right? X-rays are ultraviolet, gamma rays are ultraviolet, but what produced them is what differentiates between them. So let's look at how X-rays are produced. Here's an X-ray tube. You have a piece of metal, you have light, and you have electrons. We just saw a piece of metal, light, and electrons. What's different about this piece of metal, light, and electrons compared to what we just saw with the photoelectric effect? It's backwards. It's the directions. With the photoelectric effect, we had light hit a surface and electrons come off. With X-rays, we have electrons hit a surface and light comes off. So it's the reverse process. So this is a little harder to explain than what we saw with the photoelectric effect. If we have electrons that accelerate it turns out that electromagnetic theory says an accelerating electron must give off radiation. Accelerating any charge has to give off radiation. We'll see later when we talk about atomic models that this is a flaw with things like the Bohr model. One of the reasons the Bohr model was rejected is this theory here says an electron can only stay in orbit for like a billionth of a second and then it's gone. Bye-bye. And so we would have no atoms bonding together because all the electrons would fall into the nuclei. But electromagnetic theory says if you accelerate an electron, it's going to give off radiation. And so how much radiation does it give off? Well, its maximum radiation it could give off would be if you took the entire kinetic energy of the electron and converted it into a photon. That's the maximum it could give off. But you could also give off a fraction of that. Right, the maximum would be if you had the electron traveling, stops, all of its energy, all of its kinetic energy is converted into a wave. That would be the maximum. But if you slow it down to something that's not stopped, it would give off a lower energy. Since the energy of a photon is HF, a lower energy, what does that mean in terms of frequency? A lower frequency. So that means that there is a maximum frequency that can be produced that just depends on how fast the electrons are traveling. And then you can have different frequencies going down from that. This process is called Bremsstrahlung, which is German for breaking radiation. The radiation that's produced when something slows down. So what does this look like? I could not take the picture from your textbook because it's just wrong. I don't know, maybe I haven't checked since the school year began, but I informed them last year that the picture was wrong and they didn't take the time to change it. Here is what you get when you look at the spectrum of radiation that's produced by banging electrons into a metal target. And so you see that ramp shape. On the far right is the cutoff wavelength or the cutoff frequency. So what's that cutoff frequency? That corresponds to H times F max is equal to the kinetic energy of the electron beam. So F max is equal to the kinetic energy of the electron beam divided by H. So that's what sets the maximum frequency, or the minimum wavelength. Notice this has wavelength and it's short wavelengths over here, long wavelengths over there. Question?
Why is 0.062 to the right of 0.035 then?
You're right, there's something weird going on. I'm going to go with that's a typo in this. I didn't notice this graphic had that problem. 0.25, 0.035, 0.062 does not follow any normal sequence. You are correct. I'm guessing that should be 0.0062. I didn't do the calculations because I didn't make it. So we have a maximum frequency or a minimum wavelength that can be produced by X-rays. And anything else is just, well, it didn't slow to a complete dead stop the first time it interacted with something. And of course, the probability is roughly constant that you have, less and less slowing down. And so all of this stuff that is shown here is the Bremsstrahlung. That's the breaking radiation. But then you have another question. What in the world are these spikes? Well, those spikes are produced by electrons that were excited by this radiation, by the electrons hitting it. So we haven't gotten into the structure of the energy levels in an atom yet, right? But you probably know from other classes like chemistry that you have, for any atom, you have a ground state, n equals 1, that has some energy, and then you have n equals 2, n equals 3, n equals 4, and so on. Different energy levels that the electrons can have. And so when these electrons hit an atom, you could have the electron strikes an electron bound to the atom, and that electron just gets knocked free. It's gone. If that happens, if you have a core electron, one that's, for instance, in the n equals 1 state, and you knock it free, what are the other atoms what are the other electrons in the atom going to do if you have an electron in here went away? What's going to happen naturally? They're going to drop. So I could have an electron drop from here to here, or from here to here, or from here to here, and so on, right? When they drop, they're going from a higher potential energy to a lower potential energy. Energy can't be created or destroyed. So if they're going from a higher potential to a lower potential energy, they have to give off energy. How do they give off energy? It's in the form of a photon, light leaving. So we have, for them falling off, different energies of light that are produced. So I could have light that goes like this with energy equals HF1, or light from this. Actually, that should be a shorter wavelength. Oops. Energy, and so on. Well, we name those energies, and those are what give us these peaks. So if it goes from n equals, well, if it ends at n equals 1, if it ends at the ground state, then we say it's alpha. So things that end here are called alpha. Things that are not, oh, crud. That's wrong. They're called K, because we call n equals 1 the K shell. If they end at n equals 2, what's the name for the shell for n equals 2? Chemistry people? No? It's the L shell. N equals 3. There's a pattern to see. M shell. So if it ends, if the electron falls down to n equals 1, falls into the K shell, we call it a K line. And then we have the Greek letters. If delta n equals 1, then it's alpha. If delta n equals 2, then it's beta. And of course, if delta n equals 3, alpha, beta, gamma, it's gamma. And so a K alpha means that it ends at n equals 1, and it had a change of 1. So where did it have to start? N2, right. And if it was an L gamma, where does it start and end? Okay. It had a difference of 3 and ends at 2, so it had to start at 5. So that's what these lines are. So this says Ag for silver and then K alpha. It's falling from n equals 2 to n equals 1 in silver. And then you see the one that says K beta, that's falling from n equals 3 to n equals 1 in silver. Of course, falling from n equals 3 to n equals 1 is a bigger change in potential energy, hence a bigger kinetic energy, a higher frequency, shorter wavelength that's emitted. So that's what the X-ray spectrum is. When you go to the dentist and you get an X-ray, this is what they're doing. They have a little tube, probably has copper as its target. It shoots electrons at that copper, and based on the energy of the electrons, it's giving off Bremsstrahlung radiation with a couple of these spikes for the characteristic X-ray spectrum. And this light is ultraviolet. It's ultraviolet, our eyes can't see it, and it travels through most of the tissue in our bodies, but some of the tissue absorbs more than others. And so in that X-ray, they're basically taking a shadowgram to see what absorbed more of the ultraviolet light. And then they can see where you have things like your bones. Understand? I walk around a lot. Let's do a problem. A potential difference of 87 kilovolts is applied between the filament and the target in the X-ray tube used at the local clinic to look for broken bones. What are the shortest wavelength X-rays produced by this tube? So I have my pretty picture. This here is going to have like 6.7 volts AC. It's going to act like the filament in a light bulb. It's going to give off visible light, but more importantly, it bakes off electrons. So there's just electrons that come off of that. And then we put a voltage difference between these two. Which side's going to be positive? The side where the electrons start or the side we're trying to attract it to? Attract it to. So we're going to put a voltage source like this that's delta V is equal to 87.0 kilovolts. And then we need to ground something. Let's go ahead and ground this. It actually doesn't matter which one you ground in your diagram, but for safety's sake, it kind of matters. So you want to have, grounded thing that's more likely to be touched. So you just kind of choose where you're going to ground. And then what happens? We have electrons that come off of here. They are accelerated across. How much energy is an electron going to have when it's accelerated across an 87 kilovolt difference? This was not on the last test, but on the preceding test. Yep. It's going to be minus because the work is, let's not go through all of that now. But it's minus Q delta V. The delta V is a positive value in this case because you're going up 87,000 volts. The Q is a negative value, so a negative is a positive. So you have a positive kinetic energy. Kind of important. Technically, it's change of kinetic energy, but start with kinetic energy of 0. So we have that for the kinetic energy that the electron has. How much of that energy is going to be converted into light if we are at the shortest wavelength possible? All of it. And so we're just going to say all of this is the energy of photon. Well, the energy of the photon is equal to HF. But it didn't ask me to find F, so I'm not going to find it. What does it ask me to find? Wavelength. So we use the relationship that frequency times wavelength is equal to speed of light. Therefore, the wavelength is speed of light over the wave, or over, nice work. And so I have HC over, I solved it for the wrong thing here. Frequency is C over lambda, so HC over lambda is equal to minus Q delta V. So finally, minus E is the Q. So I have a minus E times my delta V, which was, that's the right-hand side. Or as we like to say, 87.0 kilo electron volts is equal to HC over lambda. So lambda is going to be HC over 87.0 kilo electron volts. is equal to all the work we have to do with numbers. 6.626 times 10 to the minus 34 joules times seconds. That was Planck's constant, if I remember right. C, 2.998 times 10 to the 8th meters per second over 8.70 times 10 to the 7 electron volts. And then I need to convert into joules so my units work out. So how does an electron volt relate to a joule? That's right. So now I just throw that in the old calculator. And I can't do that in my head. Sorry. It should be fourth. You're right. I was thinking milli instead of kilo. That's what you're wondering about, right? Thank you. I was thinking mega, not milli. Mega instead of kilo. I'm doing well. 2.425?
1.425 times 10 to the negative 11.
And the units are meters. Equals 14.25. What comes after nano? Picometers? So that's a pretty short wavelength. Much shorter than, of course, the visible wavelengths. I believe that this is correct. Question? I moved it over here, so it'd be times 10 to the minus 12 because that's what pico is. Right. If you put in your calculator 14.25 times 10 to the minus 12, it'll give you 1.425 times 10 to the minus 11. And 10 to the minus 12 is the pico. Okay, so we were able to calculate that. You can do that on your own too, right? Right. You just got one thumbs up. The cutoff frequency, we basically just did the calculation for the cutoff frequency, except we found the cutoff wavelength. So there's not a lot of point of repeating doing that problem. I'm out of slides. There is one thing that I want to point out that's very useful. That equation that we just did. Nobody ever told me this, and when I was in graduate school, I just had to do these calculations over and over and over again. And so I was like, well, I should just calculate what that relationship is. You had HC over lambda is equal to the energy in units of electron volts, right? That was what we just had right there. So it makes life easier if you calculate what H times C is, and you just get a simple number. So let's do that real quick. And actually, I'm going to go one step further. HC is equal to E times delta V. And I'm going to find the relationship between delta V and lambda. That is the voltage difference, how the voltage difference it goes through relates to lambda. So let's just calculate that. 6.626 times 10 to the minus 34 joules times seconds multiplied by 2.998 times 10 to the 8th meters per second divided by 1.602 times 10 to the minus 19 coulombs. What do we get when we put those numbers together?
1.23 1.24 times 10 to the minus 6.
$1.240 times 10 to the minus 6. Like that? Okay, or units. What were the units there? Meters per volt. So what I do is I put this as 1240 nanometers. Once again, I moved it 3 decimal places to get to nano. So that's where it's 1240 and why I forgot to put the decimal point. Why was this so useful to me? Because I was working with excimer lasers, and we talk about the excimer laser as, for instance, a 5 EV laser. When I say it's a 5 EV laser, I mean that the energy of the photon is 5 electron volts. And then I need to calculate, so what's the wavelength if it's 5 electron volts? And so I can just take this number, 1240, and say, well, 1240 divided by 5 divided by the number of volts is equal to the wavelength. And so 1240 divided by 5 gives me 248. And so I was working with 248 nanometer light. And so I could change back and forth between them. And in your homework, it probably will be useful. You'll have to do this kind of calculation to change from the wavelength to the energy, and just knowing that number makes it quicker. Okay, I finished a few minutes early, which makes up for a few days where I haven't finished early. Have a good day. I'll see you in lab tomorrow where we will check the photoelectric effect to see that Einstein was correct.